What is the definite integral integration by parts formula, and how do you use it? If that's a question that you've asked yourself, this is the video for you. Because in this video, I'm going to be showing you exactly what the formula is to do integration by parts on a definite integral, and I'm going to be applying it to an example so you can see what this actually looks like and how to do it yourself. If that sounds good to you, be sure to stick around to the end of the video, and this topic should be much easier for you by the end. And if you're finding it helpful along the way, please be sure to hit that like button down below and let me know in the comments below as well, so I know that you like this kind of video and I can keep making more like it. Well, anyway, without further ado, let's go ahead and jump right into the example and talk about some integration by parts. So we'll start with the formula. Again, this formula is on my integral calculus cheat sheet, my Calculus 2 study guide. Link is in the description or the pinned comment if you want to check that out. But the formula just says if we're taking the integral from a to b of u times dv, that can be rewritten as u times v evaluated from a to b minus the integral of v times du from a to b. Just like we've done with every integration by parts problem on my channel. First thing you want to start with, right off the bat, figure out what you want to make your u, what you want to make your dv. So again, kind of similar to the last example, first thing we need to do here is rewrite this in a form that we can actually apply integration by parts, which is the product of two things. Because right now we have division, which is not really going to work. So what we want to do is think about how we can rewrite our denominator to move it up out of the denominator and to make it into a product of these two things. Well, just like the last example we did, if we make our power negative, we can do that. So if we make it y times e to the negative 2y, we can move the power up out of the denominator, or move the whole term up out of the denominator. So now we have the product of two things. So now we need to figure out what's our u, what's our dv. What's the thing that we want to integrate? What's the thing we want to take the derivative of? Well, in general with integration by parts, if you have one of your two terms being an exponential like this, it's not really going to make a difference typically, as long as your power is just some constant times your variable, like in this case, e to a constant times y. It's not really going to make a difference if you integrate or differentiate that, because the integral and the derivative are both just going to be some constant times e to the negative 2y. So we don't really care which one we make that. However, y is going to be easier to take the derivative of, because if you think about the derivative of y versus the antiderivative, the derivative of y is just 1. If we're taking the derivative of y with respect to y, it's just 1. If we take the antiderivative of y, we're going to have to use the power rule, which is going to make it into a y squared times some constant. Y squared times some constant is clearly a little bit more complex than 1, just a constant number. So if we're going to make our y u, because that's going to allow us to take the derivative of y instead of the integral, that leaves e to the negative 2y for dv, with our dy in there. So then once we figured out y and dv, we need to find du and v. Well, du is just the derivative of u, derivative of y, like I said, is 1. And we do also want to keep our dy in there. dy is always going to go with dv and du. And then the antiderivative of e to the negative 2y, you could kind of solve this out the long way. You know, the best way to actually prove that this is the integral would be to solve just this one little kind of sub problem with a u substitution. I'm going to skip through those steps and just tell you the antiderivative of this is going to be negative 1/2 e to the negative 2y. And just as a quick check, we can definitely confirm that that's the case just by thinking about if we were to take the derivative of this term here, would we get back to what we had here? Well, if we took the derivative of this term here, we would have to use chain rule. Chain rule says that we would take the derivative, the constant is just going to remain here, constant times a function. The derivative of a constant times a function is the same as that same constant times the derivative of the function. So this negative 1/2 will just carry through. If we take the derivative of e to the negative 2y, chain rule says we would take the derivative of the outside, which is e to the negative 2y. Well, the derivative of the outside would be like saying the derivative of e to the x. The derivative of e to the x is just e to the x. So the derivative of the outside doesn't actually change anything. Chain rule says derivative of the outside, leave the inside alone. So we leave our negative 2y as negative 2y, and then we multiply by the derivative of the inside. multiplying by the derivative of the inside, the derivative of negative 2y is negative 2. And then we would still have a negative 1/2. Negative 1/2 times negative 2 will cancel out, leaving us with just e to the negative 2y. So that does indeed get us back to what we started with. Okay, so once we've decided our u, our dv, our du, and our v, we can plug these four things into this formula here. So doing that, we're going to be able to rewrite this original integral as u times v, so y times all this here. So I'll actually write the constant out front here. So negative 1/2 y e to the negative 2y. And that's going to be evaluated from a to b, from 0 to 1. And then minus the integral from 0 to 1 of v times du. So v times du, which is just 1. So basically just all this. Negative 1/2 e to the negative 2y dy. Okay, so then let's just leave all this stuff out here. What's outside of the integral we'll just leave alone for now. We'll deal with that in a minute. Then what we can do here, let's just kind of simplify this integral here. First of all, we have a constant which we can pull out. If we pull out this constant, pulling out a negative 1/2, the negative from here is going to cancel with that negative there, giving us plus 1/2 times the integral from 0 to 1 of e to the negative 2y dy. So now what we've done is we've applied this integration by parts formula to kind of rewrite this original integral in a form that just requires us to find the integral of e to the negative 2y dy. Well, we already know what the integral of e to the negative 2y dy is. We found it right here. We know that the integral of that is negative 1/2 e to the negative 2y. So now we can replace this with negative 1/2 e to the negative 2y. So doing that is just going to give us 1/2 times negative 1/2 e to the negative 2y here. And keep in mind, this is still going to be evaluated from 0 to 1 because we still have our bounds on our integral here. And then all this is going to remain the same. We haven't done anything that would change any of this at this point. Okay, so keep in mind what we have here. We have these, again, these two separate parts that are each being evaluated from 0 to 1, 0 to 1. So what we can do is we can kind of simplify that down into one single thing and evaluate the whole thing from 0 to 1. So basically this part here is just right here. And then we have this part here. The 1/2, the positive 1/2 times negative 1/2 is actually going to give us negative 1/4. And then e to the negative 2y. And this whole thing, we need parentheses around the whole thing now, is being evaluated from 0 to 1. Because each half before was being evaluated from 0 to 1. We can combine that if you play it out step by step. You would find that you'd get the exact same number. So now all we have to do to evaluate this from 0 to 1 is first plug in our upper bound. So just go into our equation here, and wherever we see our variable, which is y, we're going to replace it with our upper bound. So negative 1/2 times 1 e to the negative 2 times 1 minus 1/4 e to the negative 2 times 1. Okay, so that's what we get just from plugging in our upper bound. Now it is very important. You need to put parentheses around this whole thing. And then what we're going to do is then go into this whole thing again and replace all of our y's with our lower bound. So this is what we get evaluating at 1. Now we need to do the same thing with our lower bound of 0. And then what we're going to do is we're going to subtract the 2. So negative 1/2 times 0 times e to the negative 2 times 0 minus 1/4 e to the negative 2 times 0. And again, put parentheses around each half. Whatever you get from plugging in your upper bound needs to be all in parentheses together. Whatever you get from plugging in your lower bound needs to be all in parentheses together. And then you subtract the two different halves. So I'm not going to go through actually solving it from here. I'll just leave it at this point. But you definitely should go ahead, get that practice, see what you'd get of, basically plugging in all this. At this point, we just have one giant expression, which can just be plugged into a calculator. Well, I hope you're much more comfortable with how to apply integration by parts on a definite integral at this point. If you are, be sure to hit that like button down below. That's a huge help to me and my channel so I can keep making more videos like this and keep helping you learn calculus. While you're down there, be sure to check out the description where I have the link to my integral calculus cheat sheet. That should be a huge help to you as you work through Calculus 2. And if you want to keep learning about integrals and other calculus topics, go ahead and click on one of those videos over there. Thanks, and see you next time.